Hello everyone. So in this session, we'll go through flow simulation and SolidWorks. SolidWorks flow simulation on ball valve. So the exact requirement on this is I want to find out the torque on it. So how much torque is required to rotate the knob to completely stop or completely start the flow inside the valve. Okay. To deal with this, let me just browse the file so that you can get a clear idea about it. Actually, this is what we are looking for, the torque. What exactly the torque is? The rotation of ball required a certain tuning moment, right? So we know that. So that is torque, which depends upon the factors such as pressure drop and the fluid flow velocity. So what exactly the pressure drop is happening due to the flow inside the wall, and the fluid flow velocity, how much it is. So to deal with this, so we need breakaway torque as well as the dynamic torque. So what is this breakaway as well as the dynamic torque here? The breakaway torque is nothing but the turning moment required to move the ball from rest, okay, so that the flow should start, so which is maximum, right? And the formula is A into delta P, B into delta P plus, that is pressure drop is delta P here and B are constants. And about dynamic torque, the torque can be calculated from the formula using this A into delta P, and the delta P is the pressure drop, and C is again a constant. So this is what the torque which we are looking for, and there are different torques are available, so you can go through these things, that is passive, friction based torque and the dynamic torques. According to that we should calculate, and this is the formula for coefficient of dynamic torque, that is CTDH is equal to TD delta P into dq, the diameter of the valve, pressure drop across the valve, the dynamic torque. We have the factors affecting CDT, that is the valve opening, size of the valve type, and the pressure drops and the flow directions, flow profiles as well. These are the few things you need to remember, that is for actuator sizing, seating torque, bearing torques, and the packing torques if you are dealing with the valve industries who are well known of these all the formulas. And the total opening torque and the total closing torque, if you add these things you're gonna get the entire torque. This is completely different. Okay, so let's jump on to our requirement here. The same thing here, I'm concentrating only on the hydrodynamic torque. So how much we need it. To deal with this, I'm going to define the flow simulation. So I already defined it, so I'll simply explain in brief so that you can learn what exactly I have done. So just deal with this. Initially I started with the internal flow, as this is internal flow. Okay, I won't define anything. The gravity I have defined towards downwards, as you could see. That is the only change which I did here in the analysis type. And with the fluid I have taken water into account, nothing else. Flow type is both laminar turbulent as per the requirement. The wall conditions, adiabatic, no changes. Initial conditions as same, no more changes here. Okay, so this is about the wizard while defining you need to define, and this is the computational domain. You can edit it as per your requirement by using the actor trackers, otherwise by editing the values by using these all the symmetry or periodicity options. So you can even hide it and show it by using this icons. So now by using the boundary condition, I have defined the boundary conditions. The first thing is the total pressure. I haven't added any of the mass flow rate and all. So in inlet mass flow in kg per second. You can even define the inlet velocity, but here I have taken the account of total pressure of 40 bars. Okay, and the outlet pressure are defined as the environmental pressure as it is, no more changes there. That's all. So this is the initial boundary condition which I have defined. And now to create the different scenarios, what I did is by using parametric study, you're gonna get the parametric studies here. Okay, I have defined it. Just showcase it what and all I have done here. So in this parametric study, what I have done is for different angle of the knob, I have calculated the output. So I have taken the design variables by using the add dimension. Once you click on it, you can directly go to features, and from the mates tab you can choose the angle mate, and accordingly you can define the angles. You could see I have taken 0 to 90 degrees Celsius into account, from 0 to 90. So accordingly, for me the output needed is mass flow rate and the torque and the pressure drop. So these are my outputs. Though how I have defined this pressure drop by using equation codes, I'll explain that also. And the scenario is how much you want. So I have taken the 10 angle of attacks. So according to that, 10 studies, and the cool, you're gonna get the cools with respect to all the studies. If you're just using the scenarios, you can run this option where you get all the results here for the 10 degrees, 20 degrees, 30 degrees. You can simply right click and you can copy these results. Otherwise you can use, instead of, let me just showcase these things first, you can use the time history curve to get the graph accordingly. So here you can see the pressure drop for this one. So this is for this. Design point 3 is of I think let me cross check. $20 degrees. Okay, you can even have the chart how they are happening with respect to the design studies. Accordingly, pressure drop is keep on increasing as per the angle from 0 to 40. Okay, and same thing torque. So for initial breakaway torque it is more, and then again it will keeps on decreasing and then increases. And then we have the mass flow rate. Accordingly, finally it will stop because at 90 degrees it will close. Okay, you can even see this one. So there are different advanced charts available, but right now I prefer this. The torque changes, so it is for 20. The torque value is more, you could see 1.1, so which is a breakaway torque, which is anyway more to stop or start the flow inside the valve. Okay, so this is how you need to create the what if scenarios by using the flow simulation. And here you could see directly can switch between all the required studies. So this is what if scenario, the default one. I'll load the results to just showcase what and all steps we have done. Before that, goals. You could see I have defined the inlet and outlet pressure goals, and this is the equation based on it. So total pressure drop, which is equal to inlet minus outlet. So you're going to get the pressure drop value accordingly. To see the results, you can load the results and you can directly show them. So this is the mass flow rate, or else if you want to see each and everything, you can directly insert the goal can select all and show. It will show each and everything for particular study. Default study mass flow rate is this much. In this sense, it is 0° angle, and the torque required is 0.333. And then inlet pressure, outlet pressure, pressure drop. Okay, so these are the few information about this. And then to again visualize the flow, you can have the section view, otherwise you can change the transparency mode accordingly. I'll switch to other studies to just showcase the results. That is better. You can load the results accordingly. And by just taking, you can see here it is for 10 degrees. You can add the flow trajectories here for the inlet. And even you can have the animation for this. And same thing, you can switch to other angles as well. So this is for 60. Could even draw the cut plots. For just your convenience, I'm just showing it. You can select the plane, click on show. If you want, you can have it. The section view will help you to just visualize it. Even you can animate this, cut plots. Even you can have the flow trajectory animations also. Depending upon the wall location, how the flow is taking place inside, you can able to visualize it. Or if you want to take the complete model into account, you can add the transparency mode here only. You could say entire model, and you can have the flow inside it. Okay, so that's all about this session. So we have gone through everything, but one more step is remaining here, that is motion study part. So what I did is I have calculated the let me just activate the motion studies to show the results. Okay, so this is how the motor torque is generating here. This is 30 Newton meter, which is required to rotate this. To have it, you can simply play this one. So what I did is I have calculated the pressure or the force on the wall, how much it is generating due to the flow. So I have defined the same pressure by using this. You're able to see this 1976. That pressure I have defined on the wall, and accordingly I have calculated the motor torque, how much it is required. So this motion studies also will help you to get the torque required by using this. Okay, so I hope it's clear. Thank you. Stay tuned.